problems. Suppose you have an expression of the form a sin x plus b cos x divided by c sin x plus d cos x. A, B, C, D are any four constants. You are required to obtain integral of this. Suppose numbers a, b, c, d are such that numerator is exact derivative of denominator, job will be very simple. It will attain the form dt by t where denominator is t. Suppose a and c are equal, b and d are equal, then also it will be a trivial job. Otherwise, what to do? A and b are such that numerator is not derivative of denominator. Also, A and C are unequal, we do not get ordered pair ABCD, AB equal to ordered pair CD. Okay. In such a case, for example, okay, how to get the integration performed? Method will be, suppose you have two linear equations in x and y. Is the system completely solvable? Yes, because any one of the required unknowns x or y is obtainable as a linear combination of these two. By multiplying this by some number, multiplying this by some other convenient number, adding or subtracting, we can perform eliminations, we can get individual x. Similarly, individual y can be obtained. Same principle, idea we will be making use of now. If the numerator is exactly equal to the denominator, job is trivial. Numerator is derivative of denominator, job will be trivial. Catch hold of those two expressions. Try to obtain the numerator in terms of those two. So, I will try to obtain 2 sin x plus 3 cos x in terms of what you have in denominator and the derivative of what we have in denominator. Let me obtain this. It is definitely possible, as we usually perform there in solving the equations. It is possible to obtain this in terms of these, what are a and b, such that this expression may be equal to this. We need, how many signs are there on right side? 5a plus b to be equal to 2. Number of cos on right side minus a plus 5b. I want this to be equal to 3. Two equations in two unknowns can be definitely solved. You will get a equal to and b equal to. Multiplying the second equation by 5 and adding 2 plus 15, 17 is equal to 26b. B is, am I right? Then substitution or elimination of b, multiply first equation by 5 and subtract one from the other. You will get 25a minus a, 26a equal to 10 minus 3, 7. Am I right? 20. Correct. Using these values, I will be able to decompose my given required integral as a 7 by 26 into 5 sin x minus cos x plus b 17 by 26 into 5 cos x plus sin x. Once you get the numerator in this form, integration becomes immediate. Answer is 7 by 26 times x plus 17 by 26 times log of mod 5 sin x minus cos x. Agree? Yes. Suppose next numerator is an expression of the form a sin x plus b cos x. Denominator, in the previous example we had c sin x plus d cos x. Now suppose the denominator expression occurs with a power. Is the procedure applicable now also? Suppose you apply the method of or the idea of decomposing the numerator as we did in our previous example. What kinds of integrands we will be getting after splitting the given integral? In one part you will have numerator equal to c sin x plus d cos x. On cancellation it will get reduced to 1 by c sin x plus 5 d cos x. Is that easily integrable? 1 by c sin x plus d cos x. You have any methods for performing integrals of that form? Don't have? We must be having. We must have tried examples of that type. Okay, if you have forgotten, let us retry. The other part will have numerator derivative of this, denominator c sin x plus d cos x whole square without any change. Is that at least easily integrable? Yes, it will be of the form dt by t square. Let us try. Let me have specific values for a, b, c and d. What is that? So what form I want for the expression in numerator? I want it as a combination of what you have in denominator 2 sin x plus cos x and derivative of 2 sin x plus cos x, 2 cos x minus sin x. The values a and b satisfying this will satisfy 2a minus b equal to 1, a plus 2b equal to 1. Solving these, we obtain individual values for a and b as multiply the second equation by 2 and subtract. What do you get? Minus b minus 4b equal to 1 minus 2, minus 5b equal to minus 1, b is equal to 1 by 5. Am I right? Substitution of this b in this equation is 2a equal to 6 by 5, a equal to 3 by 5. Using the values, I get my integral as first portion a by a is 3 by 5 by 2 sin x plus cos x. 1 2 sin x plus cos x has got cancelled. The second portion b 1 by 5 into integral of derivative of 2 sin x plus cos x divided by 2 sin x plus cos x whole square. Now, integration of this part is straightforward. It is simply dt by t square t power minus 2 dt. Integral is t power minus 1 by minus 1. What about this? You know the methods. Divide numerator and denominator by cos square x. As a result, numerator becomes secant square x, this becomes tan x secant x, and this becomes secant x. So what? 1 secant x gets cancelled. No. Yes, one secant x gets cancelled, leaving 1 secant x in numerator, then tan x here, and 1 here, I think. Am I right? On dividing, what you are getting will be secant square, 3 secant square in numerator, in denominator 5 into 2 tan x secant x plus secant x. Right, I think. So 1 secant x common gets cancelled leaving this much. Okay, how do you handle this situation? Can we continue from here? Okay, one other idea may be, instead of dividing numerator denominator by cos square x, suppose you get numerator and denominator multiplied by 2 sin x minus cos x, something like conjugate of the expression. In numerator you will have a constant times 2 sin x minus cos x, and denominator will be another constant times 4 sin square x minus cos square x. The advantage in getting 4 sin square x minus cos square x is you can get it reduced to a function of sin x, you can also get it converted to a function of cos x. You can work with any kind of expression in numerator, either an expression involving only sin or an expression involving only cos occurring in numerator. Agree? It works. 3 by 5, 2 sin x minus cos x, denominator 4 sin square x minus cos square x dx. Next part, let me get it integrated now itself. Integral t power minus 2 t power minus 1 by minus 1. Now, this will be broken into two pieces. Part 1 will be 2 sin x divided by this, part 2 cos x divided by this. When you have sin x in numerator, you prefer to have denominator to be a function of cos x. This will be changed to 1 minus sin square x. When you have cos x in numerator, you will have denominator expressed in terms of sin x alone. This will be changed to 1 minus sin square x. Let me write the expressions. 6 by 5 integral sin x dx divided by 4 into 1 minus cos square x minus cos square x is 4 minus 5 cos square x. Okay. Next, minus 3 by 5 into cos x dx by 4 sin square x minus, within brackets, 1 minus sin square x is 5 sin square x minus 1 plus the expression which has already been obtained, minus 1/5 of 2 sin x plus cos x. What is this now? dt by 4 minus 5t square with an extra negative sign. Cos x derivative is not sin x, is minus sin x. So, exactly minus dt by 4 minus 5t square. Can we finish off? Yes, we have a formula. This will be exactly equal to dt by 5t square minus 1. Again, a similar expression, an expression very similar to what you have obtained earlier with different coefficients. Formula to be applied will be the same. Shall I leave it like this? Okay. Next, functions reducible to the form discussed by us just now. Simply write tan x as sin x by cos x, shift the cos x to numerator, you will be obtaining an expression which was discussed earlier, an expression of the form a sin x plus b cos x by c sin x plus d cos x. Can be tried. Yes. Has this been discussed already by us? An expression of the form constant divided by a sin square x plus b cos square x, have we? How method? So, this has been taken care of already. Next, this one. You are having numerator a constant, denominator a mixture of not sin and cos now, a mixture of sin and secant. It is sum of 2 sin x and 1 secant x. One normal function, another reciprocal function. What do we do? You are certainly not comfortable with the presence of secant x. Secant x occurring with sin x is not acceptable to us. Write this as 1 by cos x, shift the cos x to numerator. Okay, what next? 1 minus sin 2x. Okay. Okay. Numerator becomes cos x into 1 minus sin 2x.
Then that will be inside when it goes, that will be sin 2x by cos 2x, cos square 2x plus.
What about this cos x outside?
That you just put it inside.
Huh.
That will become sin 2x plus cos x.
Huh.
So down you have cos square 2x. So that becomes tan 2x into secant 2x plus cos x by cos square 2x.
What about that part?
That part and cos x plus sin x.
And let us not try to mix up functions of different arguments. If we bring them together in a single application, integration may become difficult. Let us have common arguments throughout.
Sin x plus cos x whole square.
Exactly. Is a type which has already been handled by us. Is of the form a sin x plus b cos x divided by c sin x plus d cos x whole square, which has been already taken care of. Good. Next, an integrand of the form 1 by a plus b cos x or a plus b sin x. You have a mixture of constant and a trigonometric ratio, basic trigonometric ratio, sin x or cos x you will have. Idea is, one of the methods is, several approaches are there. It is a comparatively very simple integrand. We have many approaches. One approach, simply multiply numerator and denominator by 3 minus 5 cos x. Easily now we can decompose the integral. We can get it as a sum of two integrals. Among the two parts you get, one part will be this, easily workable. How? Expressing the denominator as a function of sin x, for which this is the derivative. Writing this as 1 minus sin square x, we will be obtain a very convenient form. We can take the help of the substitution cos x equal to t, reduce it to a standard form and then carry out integration. What about the first part now? That also is equally simple. Only thing is, different substitution you will have to make use of. you will divide numerator and denominator by cos square x. You will see derivative of tan x in numerator, get the denominator expressed in terms of tan x and finish the job. Nine minus 25 into 1 minus sin square x. So 25 sin square x plus 9 minus 25 is 60. Here you will write this secant square x as 1 plus tan square x, apply the substitution tan x equal to t. In this case, straightforward, sin x equal to t, cos x dx is dt. Okay. Can be left, I think. Yes. Other options. I said there are many ways to handle a situation of the form 1 by a plus b cos x or a plus b sin x. One method is this. What is another alternate approach that can be tried in the same situation? One standard substitution helps which can be made use of in any situation involving sin and cos in linear form, not with degrees, is use of the substitution tan x by 2 equal to t. This is one situation where this substitution is usable. How does this substitution work in a situation of this kind? Only thing is, when you apply tan x by 2 equal to t, any sin x occurring in the expression becomes 2t by 1 plus t square. Any cos x occurring in the expression will be replaced by will get replaced by 1 minus t square by 1 plus t square. Use of half angle formulae, and dx becomes 2 dt by 1 plus t square. Actually, secant square x by 2 into half dx is dt. So, dt will be 2 dx divided by secant square x by 2. Secant square x by 2 1 plus tan square x by 2 is 1 plus t square. When you implement this substitution, integral becomes 2 dt by 1 plus t square by 3 plus 5 into 1 minus t square by 1 plus t square. Simplification is 2 dt by 3 plus 5, 8, 3t square minus 5t square, 2t square. Has the integral achieved a standard form? Yes. Okay. Which is more simple? Use of this substitution or this method? Whichever you feel convenient, you apply. Or in your examination, first have a look at the answers. If the answer is in terms of x by 2, it means this method is preferable. Answer is in terms of whole x, you follow this procedure. Okay. One more situation where I can give you more than one method for carrying out integration. One method, the method which just now discussed, use of the substitution tan x by 2 equal to t. Let me first apply that. Sin x replacement is 2t by 1 plus t square, cos x replacement is 1 minus t square by 1 plus t square, dx replacement is 2 dt by 1 plus t square, denominator 3 cos x, 3 into 1 minus t square by 1 plus t square, plus sin x 2t by 1 plus t square, plus 3. Simplification gives us 4t plus 1 minus t square numerator denominator 3 plus 3 6 2t minus 3t square plus 3t square cancel. We are a bit lucky, I think, in this case. We are not left with any quadratic term in the denominator. Normally, in general, t square term need not get cancelled. Does it remain?
1 plus t square.
Oh, one more t square is there in denominator. I forgot. Okay. Taking care of the remaining factor, 2 by 1 plus t square dt. Still, expression has attained this comparatively simpler form. In general, in a general situation, you must expect one more quadratic term here in this denominator. So, finally, the denominator becomes a biquadratic. In this case, it has taken a slightly simpler form. How to continue? Notice that what you have obtained as integrand now is a simple rational algebraic fraction. And for integrating a rational algebraic fraction, you have a unique method, the method of splitting into partial fractions and carrying out integration. Only method that you must try whenever your integrand is a rational algebraic fraction is the method of splitting into partial fractions. Okay. Is our fraction proper? Yes. Numerator is of degree 2, denominator is of degree 3. So, direct we are able to split it into partial fractions. You will get two partial fractions, one with denominator t plus 3, another with denominator t square plus 1. The one with denominator t plus 3, numerator of the one with denominator t plus 3 is obtainable by inspection, applying t equal to minus 3 everywhere except in that factor. This will be 1 minus 12 minus 11 minus 9 minus 20, correct I think, minus 20 divided by 1 plus 9, 10. Agreed? Yes? Am I right? Numerical, yes. Next, this numerator, this is numerator of partial fraction corresponding to a quadratic factor, will have two components like at and b. These coefficients are not obtainable by inspection. You have to apply your usual straightforward approach and get those coefficients to be incorporated in the numerator. Suppose that this is at plus b. On applying common denominator, you will have t plus 3 into t square plus 1 in denominator. Numerator will become minus 2 into t square plus 1. You will be getting 1 t square term, coefficient minus 2, plus this at plus b into t plus 3, which gives rise to one more term with t square as coefficient. When you multiply these two, what number you will get as coefficient of t square? A. Here you are getting minus 2. When you club these two, you are getting a. So, total becomes a minus 2. Your requirement is minus 1. Therefore, a must be a minus 2 is minus 1. A must be 1. It remains to find b. Let me collect the constant terms. This product will have constant term minus 2. When you multiply these two, constant term becomes 3b. Minus 2 plus 3b must be equal to 1. So, b must be
1.
minus 2 plus 3b is 1. b is 1. Let us cross check comparing the coefficients of t. No t term I am getting. In this product, I find t in two places. In one place coefficient minus 3, other place coefficient 1. A is 1, not minus 1. A mistake has been committed. Because of our cross checking, we could identify that. Let me once again cross check by computing the coefficient of t square minus 2 plus 1. Is it as desired equal to minus 1? Yes, everything is okay now. Is this directly integrable? Yes. What about this portion? Yes. What about the remaining portion? Yes. In this procedure, I went directly to the application of the substitution t equal to tan x by 2. Directly in the whole expression, I applied the substitution t equal to tan x by 2. I could have slightly simplified the process. How? First, decomposing the integrand to a certain extent. How an expression of this form can be decomposed? We will write, following one of the ideas used in an earlier problem, write the numerator as some constant into denominator plus another constant into derivative of denominator. This much will not be enough to cover the whole numerator because there is a constant term in the denominator. Just a into denominator plus b into derivative of denominator will not cover the numerator completely. You will have to add another constant c in the numerator as a part of it. Now, you will be able to decompose the integrand into three parts. In part 1, numerator will be a numerical multiple of denominator. Quotient will be a simple constant, integration immediate. Second portion, numerator will be a numerical multiple of derivative of denominator. It will be of the form dt by t and integration immediate. In only the last portion, none of the substitutions directly usable. Numerator will be a constant, denominator as it is, no change. Now you apply the substitution t equal to tan x by 2. Only in that reduced portion you apply the substitution t equal to tan x by 2. Your computational things get simpler. A part of the simplification process will be avoided. Okay. One more approach to get the same integration performed. First, you apply the initial part of what I was telling just now, breaking up of the integral into three parts, so that in one part numerator will be not numerator, the entire integrand will be a simple constant. In the second portion, numerator will be derivative of the denominator multiplied by a constant. Integration is through substitution. Only the last portion involves some complication. Numerator will be constant, denominator that function 3 cos x plus sin x plus 3. I will discuss how to handle that last portion, only the last portion. Suppose you get some constant k divided by 3 cos x plus sin x plus 3. Now, question is how to get this integrated. One approach t equal to tan x by 2. I want an alternate approach. You just apply one of your trigonometric ideas. Suppose you have an equation of the form a sin x plus b cos x equal to t is equal to a constant c. A sin x plus b cos x equal to c. Simple equation, but not a standard equation. A sin x equal to b is a standard equation, immediately solvable. Immediately you are able to write down the general solution. B cos x equal to C, directly solvable. Suppose you have a composition A sin x plus B cos x equal to C. You require a special approach. What is that? Divide and multiply by root A square plus B square. You will get the advantage of combining the two terms, writing the sum of the two as a single trigonometric ratio, either cos of A minus B or sin of A plus B, like that. We use that idea now. Root of A square plus B square, root 10. We will multiply and divide by root 10. Now, because this is a constant which is less than 1 in numerical value, there exists a alpha such that this is equal to cos alpha. Because this is also a constant with the numerical less than 1, there exists a beta such that this is equal to sin beta. But we have square of this plus square of this equal to 1. Therefore, alpha and beta cannot be unequal. They must be one and the same. They must be equal to each other. If this is cos alpha for some alpha, this must be sin alpha for the same alpha. So I get what is alpha? It is the angle, unique angle, such that cos alpha equal to 3 by root 10 and sin alpha equal to 1 by root 10, or in shorter form tan alpha equal to 1 by 3. Will it be a well-known angle? How many degrees? No, it is not a well-known angle. We have to retain that form tan alpha equal to 1 by 3 as it is, or at most we may write alpha equal to tan inverse 1 by 3. Okay. Have we attained a standard form now? Yes. How to integrate? Just now we have tried a similar problem. Multiply numerator and denominator by something like conjugate of this, not exactly conjugate, something like root 10 cos x minus alpha minus 3. Decompose. In one case bring in tan and secant square, in the other case direct substitution. Okay. Writing work still remains. To complete the job, I leave it to you. Another situation where the previously used substitution tan x by 2 equal to t is workable. Conveniently, without any problem, we can apply the substitution tan x by 2 equal to t, get the integrand transformed into a standard function. But because the coefficients involved are all equal to each other, especially because these two coefficients are equal, you have another approach, shorter approach. Any suggestions? Okay, one approach. This may be written as root 2 into sin of x minus pi by 2. Correct? Oh, x plus pi by 2. Oh, x, not pi by 2, pi by 4. Root 2 into sin of x plus pi by 4. Fine. So, denominator will be obtained in the form a plus b sin x minus x plus alpha. Now, you can multiply numerator and denominator by 1 minus root 2 into sin of that. Get the integrand decomposed. In one case, bring in secant square and tan, use substitution. In the other case, straightforward. Okay. Any other idea? 1 plus cos x can be written as 2 cos square x by 2. Very good. And sin x is 2 sin x by 2 cos x by 2. Good. Then you will have a common factor for the terms in denominator. What will be the common factor? 2 cos x by 2. Inside you will have sin x by 2 plus cos x by 2. Then divide numerator and denominator by cos square x by 2. Cos square x by 2. numerator will become secant square x by 2. In denominator, the cos x by 2 outside will get cancelled. Inside, sin x by 2 plus cos x by 2 will take the form 1 plus tan x by 2. Go for the substitution, tan x by 2 equal to t. Good. Any other approach? Good. Multiply numerator and denominator by either 1 plus sin x minus cos x or 1 plus cos x minus sin x, any one of the two. Let us try what happens. Let us see. Denominator becomes 1 plus sin x whole square minus cos square x. 1 plus sin square x plus 2 sin x minus cos square x. But 1 minus cos square x is sin square x. So, finally, we are getting 2 sin square x minus 2 sin x. Are you following? 2 sin square x minus 2 sin x is 2 sin x into 1 plus sin x. 1 plus or minus? What sign you are getting? Minus. 1, huh? 1 second, let me repeat. 1 plus sin x whole square minus cos square x. 1 plus sin square x plus 2 sin x minus cos square x. 1 minus cos square x is sin square x. So, finally, you are getting 2 sin square x plus 2 sin x. 2 sin x outside, inside 1 plus sin x. Correct it is. Okay. Next. Decompose. In the first part, 1 plus sin x is found common to numerator and denominator. Integrand reduces to 1 by 2 sin x. In the second part, numerator will be cos x dx and denominator 2 sin x into 1 plus sin x. Integration immediate, integration through substitution, later resolving into partial fractions and then use of standard results. I am not claiming that this is the shortest method, just one other alternative, simple alternative. Good. Next, dx by 3 sin square x minus 4 cos square x, a comparatively much simple situation. Simply divide numerator denominator by cos square x, we will be getting secant square divided by 3 tan square minus 4, use of tan x equal to t. Or if you divide by sin square, cosecant square by 3 minus 4 cot square, cot x equal to t. Same method is workable now also, but the integration will not be immediate. Some more computational exercise may be needed to bring it to standard form. We divide numerator and denominator by cos square x. How to proceed? Repeated occurrence of tan x in the expression suggests us the substitution tan x equal to t might be helpful, but immediate application of the substitution not possible because I am not finding secant square x with dx in numerator. What we do? We provide it from our pocket. Multiply and divide by secant square x. Write the denominator secant square x as 1 plus tan square x. Use the substitution tan x equal to t. On applying the substitution suggested, we will be getting 2t square plus 1 by 3t square minus 2 into 1 plus t square dt. how to work this problem? Partial fractions. And finding partial fractions will not be that difficult, because you notice that there are only even powers, even though the denominator factors of second degree, their numerators will not have two components. Each numerator will be composed of a single term, constant term only. Remember it. Let me do that job also. I will get two partial fractions, one with denominator 3t square minus 2, other with denominator t square plus 1. For the second numerator is obtained by applying t square equal to minus 1 everywhere except in this. Minus 2 plus 1, minus 1, minus 3, minus 2, minus 5, minus 1 by minus 5, 1 by 5. To obtain the second numerator, apply 2 by 3 everywhere, t square equal 2 by 3 everywhere except in this. 2 into 2 by 3, 4 by 3 plus 1, 7 by 3, 1 plus 2 by 3, 5 by 3, 7 by 3 by 5 by 3. Okay. Many problems on substitution method we have covered now. Still a few standard applications of substitution method remain. One of them is when the integrand consists of a quadratic of the form ax square plus b in numerator and a biquadratic of the form px to the power 4 plus qx square plus r in denominator. Notice that the quadratic and biquadratic have not been randomly chosen. The numerator quadratic has x term missing. Denominator biquadratic has x term, also x cube term missing. Denominator is composed of only even powers. Even numerator also is composed of even powers only. Okay. A most suitable method applicable to handle an integral of this type is divide numerator and denominator by x square. Notice that denominator will become an expression of the form px square plus q plus r by x square. Among the terms of the denominator px square plus r by x square, this sum is expressible in two ways. You can write it as root px plus root r by x whole square minus something. You can also write it as root px minus root r by x plus something. In any one of the two ways, the denominator is expressible. What are derivatives of these two expressions you find? One derivative will be, derivative of root px plus root r by x will be root p minus root r by x square. For the other, it will be root p plus root r by x square. Notice these two terms which are obtainable as derivatives of this, try to obtain the numerator in terms of those derivatives. You will be able to have a proper decomposition. From there onwards, job becomes too simple. Some exercises. To begin with, a very simple function of the particular form that I mentioned just now. Or let me have a still simpler situation. I will choose, say, x square plus 1 in numerator. Still simpler now. By increasing the number of terms, I have not complicated the situation. I have made the situation more simple. Okay. On dividing numerator and denominator by x square, I am getting this much. denominator expression is obtainable in terms of both x plus or minus 2 by x. Square plus something or minus something will be the denominator. What are the derivatives of these two expressions in terms of which denominator is expressible? Derivatives are 1 minus or plus 2 by x square. Try to obtain the numerator in terms of these two. What linear combination of 1 minus 2 by x square and 1 plus 2 by x square is going to give you the numerator? Determine. My requirement will be a plus b equal to 1 and minus a plus b equal to half. Agree? A plus b equal to 1 minus a plus b equal to half. So, what are a and b? Yes, a equal to b equal to 3 by 4 and a equal to 1 by 4. This 1 minus 2 by x square is the derivative of what? Is derivative of x plus 2 by x. This 1 plus 2 by x square is derivative of x minus 2 by x. Right? Okay. When you have numerator equal to differential of x plus 2 by x, it is preferred to have the denominator also in terms of x plus 2 by x. Okay. In this case, I will have the denominator expressed in terms of x minus 2 by x. This is a constant times dt by t square minus 4. This is another constant times dt by t square plus 4. Each is a standard integral. One more situation of the same previous type. Your first step in the evaluation of the integral will be dividing numerator and denominator by x square. Find that denominator is obtainable in terms of both x plus or minus 3 by x. Derivatives of these x plus or minus 3 by x are 1 minus or plus 3 by x square. You have to try to obtain the numerator in terms of 1 minus or plus 3 by x square. Yes.
This could be written x square plus 1 whole square plus root 8 whole square. Right. 1 by x square plus 1 whole square plus root 8 whole square.
Okay, this expression was expressible as x square plus 1 whole square plus root 8 whole square. What is the advantage?
It is directly 1 by x square plus s square.
No, because derivative of x square plus 1, what you are squaring in the first part, do not appear in the numerator. Your theorem applies only for replacements of x by linear ax plus b, not quadratic or any other type of polynomial. Clear? What coefficients? This is 1 by 2 minus 1 by 2. Not correct, I think. 3 by 2 plus 3 by 2, it will be 3. Okay, let me adjust. Now it's correct. It should have been 1 by 6 minus 1 by 6. Okay. Decomposition applied. First part has a numerator derivative of x minus 3 by x. We write the denominator also in terms of the same x minus 3 by x minus 3 by x whole square plus how much? Your requirement is plus 2, is it not? On expanding this, you are getting minus 6 plus 4. Is it not equal to plus 2? No. What should it be? Yes? 8. Next coefficient minus 1 by 6 into integral of. Now the numerator is derivative of x plus 3 by x. Obtain the denominator in terms of x plus 3 by x plus 3 by x whole square minus expansion gives you the constant term 6, your requirement is 2. Yes? Is this in a standard form? Yes, dt by t square plus 8, dt by t square minus 4. Okay. A slight extension. We have the denominator in the previous form ax to the power 4 plus bx square plus c, but numerator is more complicated now. It is not a simple quadratic of the form ax square plus b, slightly more involved. It is a cubic, arbitrary cubic. In which situation is the method that we were discussing just now is applicable? In which part of this situation the method that we were just now discussing is usable? The part with the numerator x square plus 1. Okay, let us separate that part from the remaining part. This part can be handled by the method that we were just now discussing. Divide numerator and denominator by x square. Find out in terms of which expressions denominator is expressible. Obtain their derivatives. Write the numerator in terms of those two. Decomposition method, so on, so on. Okay. What about this part? The speciality of this part is denominator consists of only even powers. Numerator consists of only odd powers. Take the advantage of that. Okay, then why all those complications? You are finding only odd powers in numerator and even powers in denominator. X square equal to t is usable. may not substantially simplify the integrand, but it will to some extent get the integrand reduced to a simpler form. Thereafterwards, let us plan afterwards what to do, how to proceed. We will think about it later. Where t equal to x square. Agreeable? Yes. How to proceed now? You know the well-known approach. Write the numerator as derivative of the quadratic in denominator plus another constant. Break it into two parts. Part 1 substitution, part 2 completing squares. Before that, you may check, is the denominator factorizable? If it is factorizable, you need not go through that longer procedure. You may simply split into partial fractions, get the integration performed immediately. But this is not factorizable. You have to depend on completing squares method. But before that, have the numerator expressed as derivative of this plus another constant. Are you in a position to finish the job yourselves? Yes. Next, some more applications where we cannot predict the use of this method in advance, but only after some kind of simplification in a later stage we will find that this is the method to be used to finish the job of integration. Looks like a very simple function. What to do? Tan x equal to t square. Okay. What will be dx? Dx will be 2t dt divided by secant square x. Secant square x is 1 plus t square. Am I right? No, I am wrong. Secant square x is 1 plus tan square x is okay, but tan square x is not t square, is t to the power 4. What you have obtained now is a quadratic of the form at square plus b in numerator, a biquadratic of the form px to the power 4 plus qx square plus r in denominator. The method, the one that we have been discussing recently, very recently. Yes. First situation, integration of 1 by sin to the power 4x plus cos to the power 4x. Guess. Okay, okay. 1 minus 2 sin square x cos square x. 1 minus half of sin square 2x. Right. Wait, 1 second. Let me write down what you have just now obtained. It is 1 minus half sin square 2x. Agreed, right?
Half plus half cos square 2x.
What are you trying to do?
I'm just taking out half there. So that I get 1 plus cos square x would be again cos.
What is the need of reducing the degree further? Have you not obtained a form which has already been discussed by you? What to do? Divide numerator and denominator by sin square 2x or cos square 2x, any one of the two. Okay. How we obtain this from this? Is it clear? Is it clear to all of you? We treated this as square of sin square x plus cos square x minus unwanted term that you are getting on squaring 2 sin square x cos square x. Sin square x plus cos square x whole square is 1 and 2 sin square x cos square x is half of 4 sin square x cos square x, which is the square of 2 sin x cos x, which is the square of sin square 2x. Okay? Divide numerator and denominator by which you prefer, sin square or cos square, whichever. Both work. Sin square. What next? Leave the cosecant square 2x in numerator as it is. Change the cosecant square 2x in denominator to 1 plus cot square 2x. Substitution, cot 2x equal to t minus cosecant square 2x into 2 dx equal to dt over. Another approach may be divide numerator denominator by cos power 4. Numerator becomes secant power 4x, denominator tan power 4x plus 1. Okay, what next? Break this secant power 4 as secant square into secant square. Write the second secant square as 1 plus tan square. Substitution, tan x equal to t is 1 plus t square by 1 plus t power 4 dt. A situation where the method that we were discussing few minutes before is able. But we have a simpler method, fine, this is okay for me. Okay, next problem. The form of the integrand must suggest use of a substitution. X equal to? No, not enough. Slightly better, advanced substitution. Cos square. Cos square 2x. So that root x becomes cos 2x and we will be able to simplify both 1 minus cos 2x and 1 plus cos 2x simultaneously. Very good. This becomes 1 minus cos 2 theta, which is simplifiable as 2 sin square theta. This becomes 1 plus cos square 1 plus cos 2 theta, which is 2 cos square theta. Cancel out common factors. You will be getting sin theta by cos theta into dx. Dx is 2, yes, 2 cos 2 theta into minus sin 2 theta into 2 d theta. Oh, just d theta or 2 d theta? 2 d theta. Okay, what next? how to get this further simplified? Sin 2 theta may be written as 2 sin theta cos theta, and then we will be able to remove 1 cos from numerator denominator. Okay, then let me write down minus of 2 into 2 4 integral of yes okay, on cancelling cos theta and combining the remaining sin thetas, putting them together, okay, one more 2 then, 8 sin square theta into cos 2 theta into d theta. Am I right? Yes. Okay. How to? Yes, yes.
1 minus 2 sin square
Write cos 2 theta as 1 minus 2 sin square theta.
multiply sin square theta inside.
Okay. And then you will be getting sin square theta minus sin power 4. Okay.
Sin square theta can be written as
That's okay. 1 plus cos 2 theta by 2. What about sin power 4?
sin square theta whole square.
Huh.
That is half into 1 minus.
Okay. Go on reducing the degrees. And continue it till you get an expression of degree 2 or 1, at which stage you can directly perform integration and get the integral evaluated. Fine. Okay. We will do it. Or instead of that, why not think of reducing the degree of this factor? Instead of writing this as 1 minus 2 sin square theta, let me leave this as it is. Already it is a term of degree 1. Let us not disturb it. Let us not try to increase its degree. We will try to reduce the degree of this using the same formula that you are suggesting. What is sin square theta equal to? 1 minus cos 2 theta divided by 2. Will it not be more immediate? Yes. 4 into 1 minus cos 2 theta into cos 2 theta d theta. It is minus 4 into integral cos 2 theta d theta is sin 2 theta divided by 2 plus 4 into, you will have to integrate cos square 2 theta d theta. There you require one more reduction of degree. That 4 cos square 2 theta may be written as 2 into integral of 2 cos square 2 theta is 1 plus cos 4 theta. Minus 2 sin 2 theta plus 2 into integral 1 d theta 2 theta plus 2 into integral cos 4 theta sin 4 theta by 4 plus a constant of integration. Is our job finished? No, integration is finished, but our job is not yet finished. We are supposed to get the integral in terms of the original variable x. That requires some computation. What is sin 2 theta in terms of x? What is our x? Cos square 2 theta. What is this in terms of x? Root of 1 minus x. Okay. Root of 1 minus cos square theta 2 theta, which is root of 1 minus x. Fine. What about theta? Cos square 2 theta is x. Cos 2 theta will be root x. 2 theta will be cos inverse root x. Okay, that is what you require. Cos inverse root x. What about sin 4 theta? Will be written as 2 sin 2 theta cos 2 theta. Cos 2 theta direct root x, and sin 2 theta, as we did here, is root of 1 minus cos square will be root of 1 minus x. Is that clear? I don't think there is any need to write it again separately. Fine. Then Next situation, dx by x square plus 6x plus 25 whole square. Any idea? Any help? Yes. Divide numerator denominator by x square. Okay. Numerator becomes 1 by x square. Denominator becomes square of x plus 6 plus 25 by x. That's all. X plus 6 plus 25 by x whole square. Good. Good. Good attempt. One second, let me record what you have suggested. We are dividing numerator by x square. Denominator becomes x plus 6 plus 25 by x whole square. Right. Good. What next? Do we find derivative of this in full in numerator with dx? No, we are not having. We are having only part of the derivative of the denominator. This part is not there. Can we supply it from our side? Later we will have to remove it. When you remove it, numerator becomes a constant, denominator this much. How do you handle that situation? Any other shorter approach? Use of a trigonometric identity. Notice that the coefficients have not been arbitrarily chosen, they have been carefully chosen only to help you in numerical computations, so that you may not deal with irrational things. Yes. If the denominator is just this much, it would have been a trivial thing, because you have a standard result which helps you in writing the integral. But now we have a power. Therefore, standard result as it is not usable, but the idea that you have used in obtaining that standard result is usable once again. How we might have derived that standard result? Integral 1 by x square plus a square equal to 1 by a tan inverse x by a. How we could have derived that? Using a substitution, x equal to a tan theta. That idea is usable even in this situation, even when you have a higher power. Use x plus 3 equal to 4 tan theta. Dx is 4 secant square theta d theta. Denominator 16 tan square theta plus 16 is 16 secant square theta. When squared becomes 16 secant power 4 theta. Am I right? This is 16 tan square theta. Plus 16 will be 16 into 1 plus tan square theta is secant square theta. Squared, okay, 16 squared, not 16, is 256 secant power 4 theta. Correct, right. Too simple, is it not? Is nothing but 1 by 64 cos square theta d theta. How to integrate cos square theta? Write as 1 plus cos 2 theta by 2, term by term integration. Okay. Once again, similar idea. X equal to 3 secant theta or cosecant theta, or you can even use a hyperbolic substitution, cos hyperbolic theta. You have the identity cos hyperbolic square minus sin hyperbolic square equal to 1, which is equivalent to cos hyperbolic square minus 1 equal to sin hyperbolic square. Even that you can make use of. Which one we will try now? Shall we try for a change cos hyperbolic? Let us see. If it does not work, we will go back to secant theta or cosecant, one of that. Numerator dx is sin hyperbolic t dt. Denominator x cube cos hyperbolic cube t and root x square minus 9 cos hyperbolic square t minus 1 sin hyperbolic t square root of that sin ht. Sin ht common cancels. Huh? Okay. Oh, did I miss anything? Huh? 3? 3 missing. Where?
Nowhere. That was not cancelled.
Huh. Is everything okay? Okay, our substitution was not x equal to 3 x equal to cos ht, it was 3 x equal to 3 cos ht dt. So our dt will be 3 sin ht dt. X cube will be 27 cos h cube t and this will be 3 sin ht. So extra coefficients both in numerator and denominator, with this 27, with this another 3. Correct? Now it's okay. And this is 1/27 of dt by cos hyperbolic cube t. How to get this integrated? A short approach I want. One method may be, okay, you suggest. Let me leave it to you. You are having 1 by cos hyperbolic cube of a function, simple argument. Suppose you have 1 by sin cube, what will you do? Or 1 by cos cube theta, what will you do? Similar approach may work now also, because hyperbolic and trigonometric work almost similarly, not exactly similarly, but almost. Suppose the situation is just 1 by sin cube theta. How will you get this integrated? Any simpler approach? 1 by sin cube theta, 1 by sin cube x. Shortest approach to get 1 by sin cube x integrated. I don't know whether it is shortest. Some idea I am having. I think that I feel that is the shortest, and I want it to be want it to come from your side.
Cos 3, cos hyperbolic 3.
You are using function of 3 theta. Okay. But it is in denominator, yes. If it were in numerator, it would have been, yes, usable. If sin cube is in numerator, yes, you will prefer use of sin 3 theta. Suppose you do not remember the formula for sin 3 theta. How do you get sin cube x integrated? Suppose sin cube x is in numerator only, but you are not remembering the formula for sin 3x. How do you get it integrated? Still there is a method. You write sin cube x as sin square x into sin x, change sin square x to 1 minus cos square x, apply the substitution cos x equal to t. What will you do now? Yes, yes. Why secant hyperbolic? What is derivative of cos hyperbolic? I want that in numerator. No. I will retain cos h. I will multiply by cos h t, both numerator and denominator. Denominator becomes cos h to the power 4. Will be written as the square of use of the formula cos h square minus sin h square equal to 1. Is this easily integrable now? dt by 1 plus t square whole square. I don't know whether it is integrable or not. dt by 1 plus t square whole square. You have a square. What you can try if the integrand is dt by 1 plus t square whole square. Cos h t. So new variable y. Okay. Our y is not cos h t, I am sorry, is sin h t. Okay. If you have decided to continue in the same direction, you do not want to change the direction, you do not want to go to the original problem and think of a different substitution, you do not want to reverse your direction, then there is a way to continue. Just think of a substitution which helps you in simplifying this. Y equal to tan theta. This will be tan square theta whole square, tan power 4 theta. In numerator you do not have secant square, you will have to provide. What will happen? Okay, it will further increase the degree of the expression in denominator, not in numerator, in denominator. So, do you think that this method is not proper? We cannot continue from here. Huh. Huh. Bad. So, we will avoid the use of this hyperbolic function in this situation where there is a high power of x occurring with the irrational function in the denominator. Suppose this were not there, this should have been an ideal substitution to work with. Because of this high power, we are coming across some complications. Let us avoid the use of this substitution. Let us think in some other direction. We have other options. We have other substitutions, usable substitutions. We will try one of them. Which one? Secant theta. Okay. Expand y power 4 plus 2y square plus 1. Okay, numerator is a constant. We can go back to that method. The method that we use to integrate ax square plus b by what? Px to the power 4 plus qx square plus r. That method we can think of. Yes, right. Dividing numerator denominator by y square, we can continue. Shall we proceed in that direction or shall we change our track? Better. Let us have one more experience, one more experimentation. So, substitution that you suggest now is x equal to 3 secant t. This will be 3 secant t tan t dt. X cube is 27 secant cube t, and root x square minus 9, root of 9 secant square t minus 9, root of 9 tan square t is 3 tan t. A lot of cancellations take place, and our integrand gets simplified to 1 by 27 integral of cos square t dt. Okay. Do we have any more problem remaining? No, this was the last, no? Yes. Good. How long I can continue? 1:30. Okay. Then few more substitutions, not essential to you. There will not be any situation where one of these substitutions is essential or is necessarily used. We can avoid the use of these substitutions. Some additional ideas I am giving. These will be covering the situations which have been already dealt by us by a different approach. For example, 1 by ax square plus b into root of cx square plus d. We have already dealt with this situation. The method we suggested was use of the substitution. Remember, x equal to 1 by t. Correct, correct. This problem is also workable by two other substitutions. Normally, not always used. Depending on the form of the answer you require, you may prefer to use one of those substitutions. So, it is better to have a knowledge of those usable shorter substitutions. From that point of view, we are discussing these additional available standard substitutions. I will give the complete list. Already known substitution is x equal to 1 by t. Now only alternates I mention. One, another, or depending on the sign of d. If d is positive, one approach. If d is negative, another approach. Both I will mention. If d positive, and if d is negative, yes, secant theta. Next, already we have one method for integrating this. Do you remember? Just rationalize the numerator. Numerator becomes x minus alpha. Denominator becomes root of a quadratic. You know what to do when numerator is linear, denominator is root of quadratic. Okay. One other method we are suggesting now. This method is even workable even when the integrand is x minus alpha into x minus beta. Next, suppose your integrand is dx by root of x minus alpha into x minus beta. Again, one method we already have, the method of completing squares. Another method, or each of these will be helpful in the evaluation of any integral of this form. In addition to the completing squares method, we have two more options. Next, root of x minus alpha by beta minus x is different from this. Here you are having x minus alpha, x minus beta. This is x minus alpha, beta minus x. Also covers root of x minus alpha into beta minus x. Also covers integral dx by root of x minus alpha, beta minus x in all the three situations. One method already known to us, rationalize the numerator, obtain the integrand as linear by root of a quadratic, so on. Completing squares. Now, alternate approach. X equal to alpha sin square theta y minus plus beta cos square theta. X equal to alpha sin square theta plus beta cos square theta is workable. In each of the three cases workable. Last one more. Sorry. M and n can be any two rational numbers, need not be integers. They can be even fractions, they can even involve fractions. For any two rational indices m and n, the method I am going to suggest now will work. And one particular situation where it is most advantageous to use that substitution is when m plus n equal to minus 2. Special use when m plus n equal to minus 2. It is usable even in general, but when m plus n is minus 2, particularly most useful. Let us practice each one of these by taking a numerical example. First case, this one. Okay. Let me first try with this kind of substitution. How to apply the substitution? We need an equivalent for dx. To obtain an equivalent for dx, we need an expression for x. 1 plus
5 by x square plus 4 equals y.
Okay, cross multiplying and solving for x square. Okay. Yes, how much? X square equal to yes, 4y square minus 9. I am just cross multiplying, separating terms containing x square from those not containing x square. 4y square minus 9 divided by x square coefficient. With the help of this, I can find a replacement for dx. Okay, what will be dx? Yes? Yes, yes. If you want the expression to be further simplified to help you in the evaluation of dx, I may get this written as yes, yes. Any help? 1 by 4 of why 1 by 4? Minus 4 times of or minus 4 into consider this 4y square part. 4y square minus 9, I may write it as 4y square plus 4 minus 13. Agreeable? 4y square plus 4 divided by 1 minus y square is minus 4. What is the remaining part? Plus 13. Little bit simpler in the evaluation of dx. What is dx? X square is this much, therefore dx will be yes, yes, yes. Direct differentiation gives me 2x dx equal to derivative of this. What is derivative of this? 13 by 1 minus y square whole square into 2y or minus 2y? Minus 2y minus this into 2y dy. But before writing dy, let me adjust for that unwanted coefficient that you have obtained here. You have obtained with dx 2x. That 2x should be shifted to that side. As a result of that, I will be getting here in the denominator 1 by 2 into x, root of this. One second, let me remove this 2. Now, root of reciprocal I have to write, I think, 1 minus y square by 4y square minus 9. Minus okay, first second fraction, right side nalli last fraction numerator. Okay, 4y square, yes, we need 4y square minus 4 to get it divided by 1 minus y square and get the quotient as minus 4. So, minus 4, that part of that is covered on getting this quotient. Remaining part is not plus 13, is just minus 5. Right, correct. So, this will become plus 5. Yes, agreed, agreed. Let us apply the substitution everywhere in our integrand. The major work now will be only applying the substitution. Later integration will not be a serious problem at all. What do we get on applying the substitution? Let me find out. Any more corrections? Minus will remain. 1 second. First one negative sign. Okay, let me do like this. Include this negative sign with the terms in denominator. This becomes y square minus 1. This negative sign is gone now. When you differentiate, you get one negative sign. That's all. No more negative signs you will be getting later. Fine. Good. Let me try the substitution now. Dx is that much. Minus 5 by minus 5y by yes, 1 minus y square to the power 3 by 2, 4y square minus 9 to the power half. Okay. Next, coming to this term, x square plus 4 in the denominator. This is x square or this is x square plus 4. Yes, minus 5 by 1 minus y square is x square plus 4 into square root of x square plus 9, root of this plus 9 or this plus 9. That means this plus 5. This is 5 by y square minus 1 plus 5. Add 5 to it. 5 by y square minus 1 plus 5. Yes, yes, yes. Root of 5 by y square minus 1 plus 5. How much?
5 y square by y square minus 1.
That's all. No constant in numerator.
5 y square by y square.
Okay, only 5y square in numerator. No constant term in numerator. Okay. Into dy. Has everything been taken care of? Yes, I think. Simplify. Oh, are we having y square minus 1 in denominator? I would prefer to have 1 minus y square. What has happened? 1 second. Minus? How much? Minus or plus? Plus 5. Y square. Okay, no problem. 1 minus y square cancel. Root of 1 minus y square remains now. Irrational aitala, alla, imagine non-real aitala. Some mistake. ಬೇಡ ಇವತ್ತು ಇಲ್ಲಿಗೆ ಸ್ಟಾಪ್ ಮಾಡು. I think we will be going on making mistakes at this moment if we try to continue. We will continue sometime later when we meet next. I think tomorrow again we will be meeting. Yes, we will continue then. I will start working the problem from the beginning itself, beginning with that substitution. Some computational error must have taken place, otherwise we won't get such non-real numbers under as part of the integrand. Its substitution is a valid substitution. It has not been properly made use of. That's all. Okay, we will try it when we meet next. All illustrations remain. Illustrations of